So this first panel is called Implementations and Real-World Use Cases. It will be meant to for the speakers to depict real situations where they have overcome situations that require the implementation of secure multi-party computation. So first I would call Dr. Thomas Schneider. He's a full professor for cryptography and privacy engineering in the Department of Computer Science at Technical University of Darmstadt here in Germany. He heads cryptography and privacy engineering group in Crypto that combines applied cryptography and algorithm engineering to develop cryptographic protocols and tools for protecting sensitive data and algorithms. He was awarded an ERC Starting Grant 2019 and an ERC Consolidator Grant 2023 for his research in the areas of multi-party computation, private set intersection, and private function evaluation. Dr. Thomas Schneider, please join us.
So, welcome. Thanks a lot for the introduction. I'm very happy that we have a bit more time because rushing through, if academics start to speak, they want to speak for half an hour or an hour. So I'm very happy that we have a little bit of time. Though unfortunately we're missing the invited speaker who kind of invented the field. Ivan Damgaard kind of was the inventor or co-inventor of multi-party computation. So I would have had a much easier start speaking right after our godfather of the field, Ivan Damgaard. But I try to make my very best. Ready to go. Okay, so I'd like to talk about some research for a private tomorrow, highlights in MPC. Perfect. So this is not my results, but the results of a brilliant team, some making it even into industry at a later point in time. And I'm very fortunate to work with an exciting research group at TU Darmstadt. So our group is called Encrypto, Cryptography and Privacy Engineering. And I relate to many buzzwords of the European Data Protection Supervisor's welcome speech in my talk. So our mission of the group is to demonstrate that we can protect privacy efficiently in real-world applications. And for that, we combine applied crypto and algorithm engineering to develop protocols and tools in order to protect sensitive data and algorithms, in particular computations on private data. Whatever we do is publicly funded, so we donate everything as open source, and all we do is open source projects that are later on hopefully picked up by industry, and in fact they are picked up by industry. So whatever we do is donated to the world as open source. A group has a long history in tools for the automatic generation of MPC. We already heard MPCs a lot about math and crypto algorithms and stuff. And this is like programming assembly code. And it's super technically involved. And developers and users don't want to write assembly code these days anymore. So our idea is, in a field started in 2004 by the legendary Fairplay compiler by Benny Pinkers and his research group back then, is that we have a developer who writes in a high-level language, think of C or your favorite programming language, what you want to compute securely, then you push the button and out comes an optimized MPC protocol which runs on multiple distributed machines. In fact, our tools, ABY and Motion, which we built as research prototypes, were even mentioned as best practice open source tools in the UN Guide on Privacy Enhancing Technologies for Official Statistics back in 2023. So we are very happy to provide base technology and tools that can be later on picked up by developers. We are happy to be funded by a lot of publicly funded research organizations, most prominently the European Research Council, which provides excellent funding opportunities to do forefront research. We also have funding by the German Research Foundation, some national funding agencies, and also collaborated a little bit with industry who donated some money. So we are very happy to be able to do such forefront research. Today, I'd like to talk about two projects we looked at. And the first one is called Private Data Exchange. So it's an interdisciplinary research. We already heard it's not just the technologists building tools. We also have to reach out and talk with other disciplines, in particular in this collaboration with IT security and law, where we collaborated with the group of Indra Speaker here at Frankfurt University. Now she's in Cologne, and she's an expert in law and digital law, privacy law, GDPR, and so on. So what we looked at is private data exchange between law enforcement agencies, more concretely between polices. So we collaborated with the Police Academy in Hamburg, who are real police people, and together with lawyers here from Goethe University and we as technologists from TU Darmstadt. So the idea or the case that we started this collaboration was in 2016, a terrorist attack happened on the Christmas market in Berlin. And the situation was that one police agency alone did not have enough evidence to go after the suspect who actually committed this terrorist attack. But if multiple police agencies would have joined their views on this particular person, they would have had in advance enough evidence to prevent this terrorist attack. So what law enforcement agencies wanted, they wanted to exchange data, but only for these criminal suspects. So they didn't want to pool all their data together, but just they want to compute the intersection of their databases. And if the joint evidence is enough to release the data, only then they wanted to learn the information. So that was their goal. In fact, there's multiple projects being discussed within the police, and one obvious solution is a centralized storage. This is called a project called Police 2020. And the idea was take a data warehouse, throw all the eggs in one basket, put all the data into one big data warehouse, hope for the best that nobody sees the data, and then do joint analysis on the collected joint data. So our colleagues here from Frankfurt analyzed the legal situation, and there's either no benefit or legal dangers of central storage. So putting all the data together is legally not allowed and is a dangerous thing to do. So there's another European proposal called IPRIS ADEP, which is a bit more privacy friendly. So the idea is the two police agencies, they don't exchange the raw data, they exchange a pseudonym of the person's identifiers. So they want to hash the identifier and send that to the other police agency. The police agency sees if the hashed identifier is in their database and then throws over their data, which is a bit better, but these pseudonyms have low entropy, so or these personal identifiers have low entropy. So also this is just pseudonymized data and requires additional safeguards, not a good solution. So what we proposed is, let's use multi-party computation, where these two jointly evaluate a function, and this function computes under encryption the intersection of these two databases, afterwards filters if the joint evidence is enough, and only then releases parts of the database to one of the parties. And our legal analysis said, this is positive. It reveals only matches satisfying legal rules. And this could be a solution under certain circumstances to pool data, but having high privacy guarantees. So of course, there's technical challenges. Like the main thing is even data consistency. Like many police reports are typed by hand and they contain so many typos and stuff. Like doing this in an automated way is still challenging. Also scalability, system costs and so on. There's a long way to go, but in principle, MPC could be a technology to solve this particular use case. And of course, this would be much more private and much more secure than the currently discussed solutions. So that was our point. If you want to do this, please talk with MPC people and please apply MPC and don't throw data in a data warehouse, which is the obvious solution they came up with. Okay, so the next one is a real-world demo that actually all of you can use later on. So this is also interdisciplinary research with experts in IT security on our side and usability at TU Darmstadt, the PSEC group, who are about peace and applying IT security technologies for peace studies and others. So this was an interesting collaboration, which was also published at WPES, which is a major workshop in this interdisciplinary privacy research. So our idea was, this is actually coming up again and again, this topic of chat control. And so when people are messaging, we want to keep our communication private. We want to use secure messengers like Signal or others. And we for sure do not want that service providers like Gmail or others can read our private messages. Especially this is concerning for sensitive jobs like journalists, lawyers, politicians, where actually even lives are at stake if privacy is violated. So for that, we have proper end-to-end encryption. which protects users from eavesdropping and also from data breaches by the providers. So we have state-of-the-art technology like Signal, WhatsApp, and end-to-end encrypted messengers. I don't want to make any advertisements for any of these messengers, but we have proper technology. So the problem is that in the EU and in the US, there's continuous discussions about new law proposals to protect against child abuse and other things that want to control our chats. This is the always coming up a discussion of let's control what people are sending in their messengers and hopefully prevent misuse of that data. So this would massively threaten end-to-end encryption. So all scientists working in this field again wrote an open letter, which was just sent out 4 weeks ago or so, and I think that many of you are nodding. Many people sitting here in the room have signed that letter, many people internationally, many of the audience online. We all teamed up and signed at least a big letter, and there was a big push from the IT security community that weakening end-to-end encryption and installing chat control measures on the user side is a very, very bad idea for many, many good reasons written in this brilliant letter. The fourth letter within 2 years or so. Like it's constantly coming up, this topic. And the thing is, even with secure messengers, users worry about communication getting compromised backdoors. We don't know if there's maybe backdoors in these systems, and it's hard to verify. So our idea was, what about if we don't send the message, but split the message into 2 secret shares, which is the basic technology of secret sharing underlying the beautiful idea of MPC, and use that. So our simple solution, which is just textbook secret sharing, allows users to securely communicate over multiple communication channels, even if some of them are completely backdoored, compromised, and broken. So our solution is fully client-side. We don't require any changes on the servers. It involves no complex math. I have a slide on that explaining this to people on the street without any background knowledge. It shows ineffectiveness of demanding surveillance from messengers because everyone can just flip coins and do secret sharing in their pocket with a simple website, locally run code. So the idea is, if I want, this is my postdoc Kasra and my PhD student Gori, and if they want to communicate securely, they anyway know 2 channels how to reach each other. They have an email address and they have maybe a telephone number where they can send an SMS or a WhatsApp message or a Signal message or a Teams message. So we know multiple communication channels to reach our person on the other side anyway. Can also be social media posts or stuff like that. And then the idea is Kasra takes the message hello, splits it into 2 random looking shares and sends one share here in this example via Teams and the other share via a Gmail email to Gori, and Gori recombines her shares. So the technology is literally flipping coins and XOR of bit strings. So the message is encoded as always as a series of zeros and ones. This is our message hello, zeros and ones. And then we flip for each bit a coin. And if it's this eagle, we send this bit as is. And if it's the number, we just flip this bit and turn a 1 into a 0 and send a 0 instead. Okay, now this sequence of flipped coins is the blue message, and the potentially flipped sequence of bits is the other message, and we send that over the 2 channels. So this is as easy as multi-party computation can get, and if you know only one share, you see a sequence of random coins, or you see a sequence of randomly flipped data. So this is one-time pad, essentially, one of the oldest information theoretic, post-quantum secure encryption schemes, even. We have an explainer video explaining this with like nice animations of 3 minutes. I don't want to show it to you, but this is pretty much self-explanatory. And we even now did a user study on the understandability, where we asked lawyers and computer scientists if they understand the concept, if they would trust such the math behind. And it was very positively perceived that people said it helped to understand the math behind. It's very simple, and simplicity wins. Okay, so if you want to go and play around with that, you can go to encrypto.de/EMC2, which is just a website. You download the code, you have a field, you type your message, you click create secret messages, and you have these 2 shares that you can copy to the clipboard and send as via 2 individual channels. And In summary, it makes no sense to survey any of the communication. People can just send multiple messages and it will be very hard to correlate these messages together and stuff. Okay, so one final slide is some lessons learned from interdisciplinary collaborations in this area of multi-party computation. So these research collaborations actually require domain experts who know the problems, who know the exact specifications of what they want to have. And I like these interdisciplinary collaborations, and most effort looking back is spent on finding a common language, or we talked about standardization. We should have a precise language to talk to each other, and it's very challenging that we all talk about the same things. We need to explain these advanced concepts like MPC to people who often have not even a background in computer science. They might be lawyers, they might be policymakers and so on. So it's very important to boil down these technically involved concepts to simple analogies or explain these. Also, technically interesting components of the solution, we better go for a simple solution rather than the most advanced, super fancy math underlying. We want to have simple solutions that we can talk about and that we can communicate clearly. Future directions in this field, from my perspective, is we still need to work on performance of advanced crypto. Scalability is important, also especially energy efficiency. If the system takes a factor 1,000 more energy, this is something which will end up on our energy bill. And of course, usability of MPC, where these tools can help that we automatically generate all this magic of multi-party computation. We should educate people why it can become a problem to give away all the data for a free service. We should also talk with policymakers even more that chat control is not a good idea and will never be a good idea. We should educate people what MPC can do these days already and what it cannot do. There's fundamental things that MPC cannot do, and we should also talk about these things. Also the system aspects and what has been mentioned. Okay, with that, I'd like to conclude almost in time that MPC allows to protect privacy and even intellectual property. You can even hide the function that you're computing from some of the parties, right? You can also have intellectual property protected with MPC. It's not only they all know what they are computing and we only protect the data. No, we can even go into the direction of private function evaluation where we protect the classifier or the function that's being computed. And we don't have to release that to all parties, which would hinder some use cases. Especially interdisciplinary collaborations allow to explore several application domains of multi-party computation. And what I think is very important, and I'm very happy that this is the case, that we need publicly funded research, not only industry-funded research in this area, but we need to explore also where MPC can contribute to the common good and explore new ideas without having to look at the money all the time. And we are very generous funded by the European Research Council, and I thank all our funding agencies for that, and look forward to the discussion afterwards. And thanks for your attendance and your being here with us.
Thank you very much, Professor Schneider. So we'll now move to a different presentation. Let me get my notes. So now we'll have Vincent Dunning. He is a researcher in the Applied Cryptography and Quantum Algorithms Department at the Dutch Organization for Applied Scientific Research, TNO. He studied cybersecurity in the University of Twente and is specialized in privacy-enhancing technologies such as multi-party computation and zero-knowledge proofs. A large portion of his work at TNO has been focused on practical MPC protocols for jointly combating money laundering across financial institutions in the Netherlands. Thank you very much, Vincent, for being with us.
All right, I think everything is set up. Thank you very much for having me here today in this nice event. I work at TNO, which is the Dutch Organization for Applied Scientific Research. So we basically try to bring new technologies that are being studied in universities to, well, companies in the Netherlands. And in this case, we are talking about MPC, and we did quite a number of projects on MPC with financial institutions. One of these projects is called the Alliance for Privacy Preserving Detection of Financial Crime, which is a collaboration between us, 3 of the major banks in the Netherlands, CWI and Transaction Monitoring Netherlands. And the main or the core question is how can we improve collaboration amongst financial institutions in detecting financial crime using privacy enhancing technologies? And one of the core components of this collaboration was a pilot with a decentralized algorithm using MPC to detect money laundering across financial institutions. And to illustrate a bit what the challenges that the financial institutions are dealing with in the Netherlands is that they have a very limited view of what actually happens in their transaction networks. So suppose we have a network of transactions where all the nodes here are bank accounts, and then we have the edges, which are transactions. So you can, for example, see that bank account 1 makes a transaction to bank account 3, receives a transaction from bank account 6, etc. If we then zoom in and look at only what the blue bank in this case can see, we see that, of course, it can see what its own customers are doing and with whom at other banks they're interacting, but they cannot see what the banks of other customers are doing. This is not even allowed. They are not allowed by law to share information about their customers with other banks, which makes it very easy to do money laundering. So for example, if you look at what a complete view of the transaction network could be, it could look something like this. So you see many more accounts that the blue bank cannot see. And if you zoom in even further, then you see these kinds of patterns, which are very typical for money laundering. So you see sort of cycle that ultimately comes back to account 1, but the blue bank doesn't know it, the red bank doesn't know it, the green bank doesn't know where the money came from originally. So nobody is able to detect that this is actually very suspicious. And for example, if we look at money laundering, then what happens is, for example, that the blue bank would see that account 1 receives a lot of cash, which is risky, but is not able to tell the red bank in this case that this is risky money, and therefore, well, the financial crime cannot be detected by these banks at all. So we thought, what if we can use multi-party computation to allow these banks to share this information, but then in an encrypted manner, so that no bank actually is able to see in the clear what accounts at other banks have what risks. And we use a technique for this called homomorphic encryption, or distributed homomorphic encryption to be even more precise, which on a very basic level contains a public key and a private key. The public key can be given to anyone to encrypt values. In this case, we encrypt risk scores for each of the accounts. And then there's a private key that should be kept private that can be used to decrypt a message. And there's some structure in the encryption scheme that allows us to perform computations on the encrypted values, as we already heard a couple of times before today. That's the core concept of MPC. So in this case, we used an additively homomorphic scheme, which means that we can combine encrypted values to obtain additions of the underlying values. Well, this is an illustration. So suppose you have two values, 5 and 3. They are both encrypted. Then the encrypted messages can be combined and then decrypted to obtain the ultimate result, which is 8. So how did we use this to increase the detection of financial crime with these banks? So for this, we developed this algorithm called risk propagation, which I will briefly explain how it works. So the first step is to actually set up the keys. I already said that we use distributed homomorphic encryption, which means that there's no single decryption key, but that each of the parties in the system get a sort of partial decryption key, which means that only if they all work together and all decrypt a partial decryption and combine those, then they can actually decrypt the original message. But if one of the parties doesn't cooperate, then nobody can decrypt. And this turned out to be very important in the pilot because this ensures that all the parties at least retain some form of control, that nobody else is able to decrypt the messages without everyone's consent. So this gives some certainty. Then everyone uses the public key of the encryption scheme to encrypt the risk scores of their own accounts. In this case, what we did in the pilot was simply the ratio of cash that they received over a certain period of time. So they encrypt these values and send them to the other banks. So there's some communication involved between all the banks. And then each of the banks can compute a new updated risk score for each of their own customers in an encrypted form, so they don't see anything yet. So the intuition here is that if you receive a transaction from a very risky account, then the risky account transfers some of that risk to the recipient of the transaction. And therefore, an account that receives a lot of money from risky customers from other banks will get an increased risk score in the, by doing this computation. So they'll compute these updated risk scores, and then with consent of all the banks, they can use these partial decryptions to see the updated risk scores for only their own customers. And what can, for example, happen is then that the green bank in this case sees that one of their accounts got a much increased risk score via this computation, doesn't know exactly where this risk score came from, but this can lead to, for example, further investigations about this person to which this account belongs. In the end, we managed to set all of this up and run a pilot in the Netherlands with these banks, where we actually saw that, well, we did it in multiple steps. First, we used the algorithm to do it only on their own data sets, so see what could they potentially learn from this if they only had their own data. Well, we saw not a lot of improvement. And then we were able to show that if they collaborated with, in this case, we did with 2 banks, then you actually saw a positive increase towards the customers that were risky within their organizations. But this took quite some while. I think in the end, it took us around 3 years to set this whole pilot up, even though the technology was basically already there at the start. So I would like to share some lessons that we learned from executing this pilot in the Netherlands. So on an organizational level, I think some of these topics have already been touched upon in the previous talks. But what turned out to be a major dilemma is how to do the data protection impact assessment, or DPIA. This is something that you need to do if you potentially are going to, well, hurt personal data. But in this case, the big challenge was how to have something that all the parties that are involved agree on. So in the end, what we had to do was that we ourselves at TNO, who were not part of the pilot, had to come up with a sort of general impact assessment of the technology. And then both banks individually had to come up with their own, basically, changes to it and then get it approved within their organizations. What we also heard already before is that it's very difficult to talk to people who think more in legal terms about what this technology does, who owns the data, who processes the data, whether it's even personal data. That's, I would say yes, but not everyone agrees with that. And also the way of working between the organizations is very tricky because even though they can agree to perform this MPC protocol together, there are still many other things that they are not allowed to discuss. So for example, they were not allowed to discuss how to define the risk scores. So ultimately we had to settle for something less satisfying, namely only the cash ratio, even though there are many more factors that they would normally take into account to judge which customers are risky, but they are not allowed to tell each other due to competition law. Also, data interoperability was a major challenge because, again, this was something that you cannot discuss openly amongst financial institutions, at least not in the Netherlands. The infrastructure that we needed to set it up. And as I said, this is difficult to discuss together. And finally, on the MPC side, so in the end, we were able to run this pilot with over 6 million accounts within a day, including the key generation. Actually, the key generation turned out to be the most costly part of the entire computation to get this distributed keys set up. We learned very clearly that even though some things work very nice in theory, in practice, it works very different. For example, again, the key generation, there is some randomness that the parties need to communicate to each other to generate the keys. And in theory, you would want to communicate as little of this randomness as possible, but in practice, it turned out to be better or more efficient to just send way too much randomness to each other and then not having to communicate ever again. And, well, send potentially a lot of things that you are not going to use in the end. After the pilot, we also learned that output privacy, which is, I think it should be a hotter topic in MPC research than it is right now. But MPC guarantees only data protection during the computation and that you do not leak anything about the inputs. But it doesn't say anything about the result that you get in the end. which might very clearly still leak information about the inputs. So if you look at our own pilot, for example, if you only get one transaction from one other account and you see that your risk score goes up, then you can pretty clearly guess where the risk comes from. So output privacy turned out also to be a bottleneck for us to do proper investigations, because they couldn't go into individual customers and could only analyze the results on a more aggregated level. But even then, in the end, we think it was a success, because we were able to show that we can get improved insights by doing this collaboration, which hopefully one day will lead to, well, more pilots where we can actually do proper investigation of the results. Thank you.
I would now ask Armand to put the presentation for Riivo Talviste. He's a senior security engineer at Cybernetica AS, where he has been working for 14 years on the practical aspects of multi-party computation. He has been at the forefront of several multi-party computation deployments that work on real data. Riivo received his PhD from the University of Tartu, with his research centered on the practical lessons learned from applying MPC in real-world scenarios. At Cybernetica, Riivo leads the development of ShareMind MPC, one of the earliest secure multi-party computation platforms. Thank you very much, Riivo.
Thank you for inviting me. So, yes, hi everybody. I'm Riivo, product owner of ShareMind MPC, a practical MPC implementation from Cybernetica. And I'll start from the beginning. MPC as a technology was invented actually 40 years ago already, but then we took some time before we actually learned to use it in practice. And I guess, well, I couldn't just like give a talk about deploying MPC in practice without mentioning the famous Danish sugar beet auction of 2008. So this is considered the first practical deployment with real data using MPC. But both before and after that, deploying MPC has been like riddled with two main concerns. One is, of course, performance. It's a distributed technology, network bound. So there's usually about 2 orders of magnitude performance penalty that you have to pay. But as you have heard, and also I'll give some examples, this doesn't make it impractical. There are like lots of use cases where it can be used very efficiently. And the other concern is complexity, both in deployment and in the skill set required, because usually cryptographers have to be involved when deploying MPC. And this directly translates into higher cost. So I'd like to highlight a couple of deployments from our journey in deploying secure multi-party computation technology to show how this has evolved through our eyes. So for us, for ShareMind MPC, the first practical deployment with real data was in 2011, when it was used for financial benchmarking of the Estonian IT companies. And while the data volume there was really minimal, then what made this important is that, to the best of our knowledge, this was the first deployment where the actual MPC protocol was run over the public internet. Next, there's the deployment from 2015, where MPC was used to securely link together 2 government registries. And this really like exemplifies that MPC can be in fact used to process practical data volumes. So from one ministry, we got over 10 million tax records, and another ministry, the input was 600,000 education records. And those 2 data sets were then joined together under MPC, then aggregations done on the joined data set under MPC, and also histograms and other output statistics computed under MPC. What's also important there is that the actual analysis was prepared and conducted by professional data analysts, not cryptographers. They used this R-like tool to basically conduct their work. Then it the deployments followed, where we used MPC also for fraud detection and some machine learning. But finally, I'd like to point out the deployment from 2023, where ShareMind was used for privacy preserving analysis of tumor treatment radiotherapy data. And the data sets actually came from two hospitals. One is Ludwig Maximilian University Hospital here in Germany, and the other is Gemelli Rome. And what makes this a very important milestone for us personally is that we actually didn't have to do anything. So the customer just licensed the product from us. We, of course, provided some documentation, but they did the deployment themselves. They wrote the actual analysis programs using the developer tools that we provided. So it kind of shows that you can package MPC as a product in a box that you can just take off the shelf, which is like for us as a technology providers, a really, really important step. As I have been personally involved in several of those deployments, I can safely say that actually deploying MPC is difficult. So, and it presents a number of challenges. First, there is this actual technical deployment. Since by definition, the computing parties have to be independent, then there must not be any single system administrators who actually sets up all of the computing parties, which means that there's this weird communication and coordination going on between the system administrators, and this takes just a lot of time. Also, the coordination work that the project manager has to do is quite involved because it's a distributed technology, the number of parties increases, and you have to coordinate those. Not to mention legal work, but I won't go into details there because I think the second panel today touches upon that. So, and it's fine to do all of those things very costly time-wise things when we are doing pilots with MPC, testing out new technologies and so on. But I guess if we ever want MPC technology to become ubiquitous, so it's everywhere and we don't even think about it anymore, then we need something really cost-effective, more cost-effective. And I claim that one way how we can bring the cost down is not to reinvent the wheel every time. So if you ever want to actually use MPC for any use case you have, you actually want to compute something, then please don't start by writing your own MPC protocol. There are actually numerous, dozens of options out there, different MPC protocols, bigger components, platforms, frameworks, you name it, with different maturity levels, security guarantees, support, and so on. So I've here linked a recent state-of-the-art study that may help you with that. And next, I'd like to point out two projects that actually follow along this line of thought. The first is Carbon Stack. It's an open source MPC platform developed under the Linux Foundation Europe. And what it tries to do, it tries to automate a lot of the deployment process involved in using MPC technology. And it does that by employing cloud-native technologies. So, and we are also working on integrating our ShareMind MPC protocols into Carbon Stack to offer our paddle-tested protocol suite as one option for the actual MPC backend. I won't go into more details here because I hope that Hossein will cover carbon stack in more detail. So I'll continue with the other example, which is an ongoing project with Eurostat called Joconde. And in this project, we are designing an MPC as a service solution for official statistics. And the motivation is actually quite clear. So there's an ever-growing amount of microdata. The data becomes like more and more granular. And this is very good source for official statistics, very valuable a data source. However, since it's very granular data, it also tends to be sensitive. Another example is that I think one of the jobs of Eurostat is to foster collaboration of different statistical authorities of the member states. And one way to do that is to make it easier to do cross-border statistics. So these both are very good use cases for MPC. And there, of course, has been several pilots, but Eurostat is also recognizing that if we need to do this very expensive deployment, legal work, and all of this coordination for every single use case all over again, it's not just going to cut it. So Joconde is designed to be a single deployment operated by Eurostat, and it provides the users of the system, which are the statistical authorities of member states and Eurostat itself, common open source components that deal with user access and task management. Also, Eurostat as a system operator for this Joconde has sets up a pool of MPC computing parties that it has vetted. And moreover, the Joconde system also provides templates for legal agreements. So now what the users of the system, the statistical authorities, if they have a new idea, a new use case, then they come together, they just pick data sources, define the algorithm that is going to be computed on those data sources. They distribute roles among themselves. So input parties are the ones who own the data, output parties are the ones who receive the computing results, and so on. Then they pick the suitable set of computing parties and also the actual MPC implementation that with its security guarantees that suffices for this use case. And all this together, this list is what we call a computation task specification. This gets signed by all of the participants and deployed on the Joconde system. And now the Joconde system pretty much automates everything from this point forward, except, of course, the data owners secret sharing and uploading their input data. But other than that, they don't have to worry about access management, task lifecycle, and things like that, or data retention or whatever. So it's an ongoing project, but there are several documents already published on this website, so you can have a look. And with that, I thank you.
Thank you very much, Riivo. We're actually now really on schedule, which means that we've been stretching a bit, but no worries. We'll going to move to the last panelist from this last speaker from this first panel. That is Hossein Yalame. He's a researcher engineer at Bosch Research in Renningen, Germany. He holds a PhD in computer science from TU Darmstadt and works at the forefront in privacy-enhancing cryptography, focusing on multi-party computation and zero-knowledge proofs. In 2024, he was awarded with the GDD Science Prize for Young Academics for his doctoral dissertation, Advancing MPC from Real-World Applications to Lookup Tables-Based Protocols. Thank you for being here.
Perfect. Thanks for the introduction. So let's have the slide first. Perfect. You heard now about Carbon Stack. So now I want to explain what is Carbon Stack, what we did it in Bosch, and then what happened for Linux Foundation on Carbon Stack. Perfect. So here is Hossein Yalame. That's me. I'm an MPC research engineer at Bosch. I did my PhD thanks to Thomas into Darmstadt. And my expertise is like MPC and the knowledge proof mainly. And I did a great job in my PhD because of this award and nominations. And also in my free times, I'm also reviewing a lot of papers for top conferences to be sure we have top paper and top conferences and not AI writing reviewers. So that's my one of the duties, which I like to do. Perfect. So I think all of us know why MPC is important. But here, imagine we are in a laboratory. We want to analyze some data, but the data is really dangerous. We cannot touch it. So we need some tools. Our tools here is privacy preserving technologies and especially MPC. And why is important? Because we have a lot of rules like GDPR in Germany, in Europe, we have a lot of rules in other countries also. And 71% of countries, they already have a lot of this kind of rules like China, US, India, Japan. So we need some tools to also preserve our privacy. And especially in this stage, everyone talking about AI. We will have a EU AI Act from August, so we should also care about our privacy there. So which kind of tools we can use? One tool should be like computer encrypted data or mobile encryption or MPC, perfect. The other tool could be something like based on hardware, which I don't like it because you should have trust the hardware. You have substitution attacks there. So we are mainly work on encryption and also mathematically proof techniques like MPC. So what we did in Bosch, we use MPC for some application, especially for people analytics. What that means, you know, Bosch is a huge company. We have like 400,000 employees, and we have like 60 branches in 60 countries. And we cannot just see the employee data because we have some rules in China, some rules in Germany. We cannot just share the data. So we need some solution there, which we use MPC there. And also the other solution which we are working on, federated learning. For example, imagine you want to train some cancer detection model between Germany and China. There's a lot of rules. We cannot share our data. It's important. We cannot also use FL because pure plain FL is not private. So we need also a solution there, which we use also MPC for federated learning to make FL is also private. So what we did now and what we can do by using Carbon Stack, MPC, we can have a lot of application, like we can have virtual data pooling, we can just pull the data and use it. We can have like secret management, we can have like private correlation and also collaborative training, thanks to MPC. And the other thing which we consider is cloud native technology. And if you want to use MPC, we should also have it compatible with cloud native technologies because we want to have like scalability, resiliency, and also manageable and using cloud-based systems. So because of that, also one point, we also went to open source because we want to have everything open source. Why? Because we want to reduce that cost share risk. We want to have improved quality. We want to have increased trust between the committee and also for Bosch brand on that time. Cool. Now for Carbon Stack. So we combine MPC and cloud native technology together, and we create Carbon Stack at Bosch. I would say it's developed by Bosch, hosted by Linux, and yeah. And so what is Carbon Stack? So in Carbon Stack, we have outsourcing model, as you also heard about that. So you have some clients, they will just share the data to some servers, committee parties, they can do the analysis for you. And for Trust model, currently we have active security and also dishonest majority setting, but also the other partners, they are also working for other security models. And we also have the online offline model, which you can do expensive operation offline and then having efficient online phase. And in Carbon Stack, we have different building blocks. That's for like Kilishko and timers, which we are having that randomness generation offline phase there. We have some data stores like Amphora and Castor, which we just store the data secret share and the randomness data there. And we also have ephemerals, which we are doing MPC computing parties there. And by using them, then we can provide a lot of applications like data analytics, machine learning, predictive learning, and all other stuff. And here, as you can see, so we have our cloud native technology, we have our MPC, we have carbon stack, and now welcome to different applications, healthcare, automotive, human resources, and we have all these primitives there. And how it works exactly, you have a client, then they will just share the data to some multiple virtual cloud, then they will just connect together, they will use our service, and then they have encrypted result at the end. And what you can do now, if you are a company, if you want to collaborate with others, or if you want to do some analysis of your data, you can now just share your data, encrypted data. We will do the analysis for you, and then we will send it back using MPC. And now, what happened? I think you heard. So, first of all, we have MPC ecosystem now with Carbon Stack with a lot of partners, especially with Cybernetica, from Riivo, SAP, Honda on that time, and also recently from CDPG from India, which they are doing also data for public good in India. And how that mission started in 2017, it's around 8 years ago, it was just internal project. And in 2021, they decided to, that means Bosch decided to go for open sourcing. Why they? Because I wasn't there. I was with Thomas on that time. And then in 2021, they have the community building with different partners, as I mentioned, like Cybernetica, Resolve, and other ones. And end of last year, we donated Carbon Stack to Linux Foundation to provide open MPC ecosystem. Again, is developed by Bosch and hosted by Linux. And now the partners can work on it, and then we want to make MPC great again. And that's it. Perfect. Thank you. If you have any question, I'm here.
Thank you very much, Hossein, and I hope we do have questions. I would like to present first our distinguished moderator, Giuseppe. Giuseppe D'Acquisto is a senior technology policy advisor for the Italian Data Protection Authority. He holds a degree in the electronic engineering in electronic engineering and a PhD in computer science. He is the national delegate within the technology expert group of the European Data Protection Board, the EDPB, and the internal working group on data protection in technology. He is a professor in artificial intelligence at the University Luis in Rome. Thank you very much, Giuseppe, for being here.
Thank you, Victor.
Giuseppe is going to moderate this this panel. We expect, of course, your questions to be addressed to the panelists, so as well as from the live audience. So please, if you have questions, raise your hand and we'll bring the microphone to you. Thank you.
Thank you, Victor. I don't have a presentation as moderator of this question and answers session. Maybe before starting with the questions, I will try to select the key messages from the presentations, which, by the way, I enjoyed a lot because they give the picture of a very, let's say, hot topic and, let's say, vibrant research environment. What has attracted my attention during your presentation are the following points. First, apparently we need a conceptual alignment between specialized sectors. We come from different angles of computer science, and we tend to give different names to the same items. So a common language is really needed in order to tackle the complexity of secure multi-party computation. It's a powerful tool for the decentralization of processing operations, and especially this brings the benefit of, let's say, overcoming the difficulties of a single point of failures or single point of trust that normally we have in centralized environment, and this is very relevant in cloud environment. I take the message that secure multi-party computation is a security engineering tool, which is meant for input privacy, essentially for providing confidentiality in the computation. It's not for statistical disclosure, and disclosure is an extra, let's say, an orthogonal element of exposure for the results of computation. Now, it is debatable whether these techniques are anonymization techniques, which is a very important aspect for regulators, as me, as Victor, as other people coming from the data protection authorities in Europe. For sure, they are privacy enhancing technologies, what we call PETs, which are there to, let's say, reinforce the implementation of principles that we have in Article 5 of the GDPR. They are there to make the implementation of principles more effective in line with Article 25 of the GDPR, and in particular, the confidentiality principle, the purpose limitation principle, and the minimization principles. And if the implementation, especially of the minimization principle, is so well, let's say, put in practice, maybe these techniques may also become anonymization techniques, but this depends also on a number of contextual factors which have to be assessed case by case, also in the light of the recent ruling of the European Court of Justice on the notion of pseudonymization, which, let's say, needs some extra effort. It has been a topic which has intersected the attention of data protection community in the past. The ENISA has, in a series of reports, included secure multi-party computation among the pseudonymization techniques, and the EDPB has included secure multi-party computation as one, let's say, additional technical measures which can enable the transfer of data towards countries where the implementation of the legal framework is not aligned with the European one. So we need some supplementary measure in order to provide extra safeguards to European citizens. This is the environment where, from the perspective of data protection authorities, we should look at these very promising techniques. Now it comes to questions. So my first question comes from a personal curiosity. Also, listen to your talks. I got the impression that secure multi-party computation is adequate to solve specific problems, namely private sums or private set intersection, or detecting CSAM materials, which maybe are already known by comparison of hashes. Now, my question is it correct, or can we expect secure multi-party computation also to solve general problems? And as a consequence of this, should we expect a slow progress of this science, or a fast one, maybe driven by more general problems to solve? This is the first question that I ask to you all.
So first of all, the first MPC protocol published, YAO 1982 or 86, depending on how you count or which footnote you take, was showing that you can compute an arbitrary computable function securely with MPC. So MPC can in general compute everything which can be computed in polynomial time. And we have actually all these compilers today. You can compute literally anything. Like, specify what you want to compute securely, in a high-level program, think of a C program where you have the inputs, you can have for loops, you can have even arrays, you can have all kinds of data structures, and you can, with MPC, you can compute everything securely. The main question is it a good idea to compute things securely? You talked about statistical disclosure, or you can even add under MPC differential privacy. You can even perturb the results, that the result doesn't leak any sensitive information about your input data. But in general, we have tools even and compilers where you can compute literally everything securely, not only private set intersection or set sums. For these, we have even more efficient linear complexity protocols, which are super fast. But in general, you can compute whatever you like with MPC, and the techniques are there, even the tools are there, and ShareMind and Carbon Stack, all these general frameworks, they can compute literally everything securely.
Okay. Yeah, so I agree. Of course, there are indeed general purpose MPC protocols. I think the main challenge with them is that without getting too technical, they typically require your functionality that you want to compute to be represented in some intermediate representation, and that can become quite big if the functionality is not super. If the functionality is difficult, then this representation can get very big, and the resulting protocol can still get quite slow, even though the MPC protocol that's underneath it is able to compute general functionality. So what we see is then that you can, in practice, gain a lot by researching what do I really need for this particular functionality that I want to build, and optimizing your MPC protocol towards it. And then I guess the main trick is then what was presented also by Cybernetica is then to reuse those components, because a lot of the components also that we develop, for example, in this pilot, are just as good applicable to different use cases, different scenarios. So yeah, I think that's my nuanced answer.
Yeah, perfect. So first of all, as Thomas mentioned, we can MPC as like a complete Turing machine. You can do whatever you want. And I have one example. For example, 2019, my first paper with Encrypto, it was like MP2ML, one framework to have private inference of ML models. And we did something like MNIST dataset, like theory layers models. I was really happy. It was like 2 minutes. I was like, oh, perfect, that's practical. But now, like 1 week ago, we had some research. We can have Llama model, transformer models in MPC, online time less than 10 seconds. So that means it's always progressing and progressing. And I have a hope we can have really good numbers for really, really practical applications in the future also. As you can see from MNIST, 3 layers, 2 minutes, now we have something like transformers in 3 seconds. So you can see that it's progressing.
Yeah, I think we are not going to fight here. So we all say the same thing pretty much, that you can do everything under MPC. So you can have full pipelines under MPC. For example, in statistics, you can do this from extract, transform, load to linking and aggregations, and even, yes, statistical disclosure control under MPC if you wanted to. The main question is that whether it's a good idea to do everything under MPC, and in most cases you want to keep this like a portion minimal, because there's a some overhead at least.
Okay, so I understand that theoretically everything is possible, but not always this is a good idea. So when does secure multi-party computation constitute a good idea? When is the overhead manageable in computation? In which circumstances? Low scale, manageable delays. Tell us what can be the game changer in the implementation of SMPC in practical applications.
Well, it doesn't have to be like the data volume, because if you have like this, for example, optimized protocol, for example, a vectorized protocol, then the data volume is usually not an issue. It's just that it really boils down to really like specifics of a use case, whether something makes sense. It makes sense to do something under MPC. I think the general rule is that do as less as possible, but the things you like, that the parts of the algorithm that touch sensitive data, these of course have to be done under MPC. But if you can do the rest openly, so I guess that's one way to look at it.
Yeah, as you mentioned also, I would say, yeah, we mentioned we can use MPC everywhere, but in these days, for example, we cannot use MPC for real-time applications. For example, in the cars, if you want to have like privacy preserving automotive driving, if you want to catch that, for example, one passenger there's, it should be less than milliseconds. So MPC take like a minute. So you will see, you will kill it, you know. But for something like, for example, you want to see if I have a patient, if you have a cancer there, I don't want to reveal my data, then I can use MPC there. I can wait for like 1 hour, then I have the results. So at the moment, real-time application, I don't see the hope, but for other application, there is a good hope for MPC. But not just MPC. If you cannot use MPC, you can also use HE. You cannot use cryptographic techniques because it's expensive. So there is no other way for other techniques, but yeah, hopefully in the future.
Yeah, I hope I didn't say that. I think that there are many cases where MPC is not a good idea. I meant to say that fully general purpose MPC is not always a good idea because you can optimize quite a lot in practice if you carefully look at what you actually need for your use case. And I would still call that MPC, but not fully generalized.
So in general, for the MPC, you need two parties. Like if there's just one party that holds all the data, everything gets trivial. If one party is willing to share the entire raw data with another, and it's a matter of the trust model of the deployment scenario. Essentially, you need at least two parties who have mutually, they want to collaborate, but they are not legally allowed or do not want to release the data to each other. And the main bottleneck in MPC is the communication. So you must be willing, at least between these compute nodes, to send megabytes, gigabytes, maybe even terabytes of data back and forth. But many parties can provide their inputs in a secret shared form, but you need to agree on at least two parties who run the MPC at some point.
Now, another question before giving the floor to the audience for other, say, curiosities which may come out. The impression that I gathered studying SMPC is that they rely on rigid protocols, meaning that if we look at the classical example of private sums, if I want to be the n+1 addendum in a sum, I have to start from scratch and renegotiate the protocol among the computing parties. This makes the, let's say, evolution of the computation rigid because you cannot enter the environment on the fly and exit from it whenever you want. Is there an avenue in research which you are aware of where someone is studying a sort of dynamic way to enter and exit the SMPC environment on the fly, making this, let's say, smoother and easier to use for, let's say, maybe real-time or semi-real-time applications? Are you aware of this? Can you give us an insight on this?
So actually, there's research on that. The concept is called, as you said, dynamic MPC or fluid MPC, where you can add and remove computation parties on the go, essentially. There's just been a recent paper at ACM/CCS this year, which is one of the major security conferences. And the research is like 3-4 years old. People are working on that. Of course, this has to be optimized. But in general, the solutions or the protocol ideas are there. And this just has to be optimized in the future.
It's possible.
It's possible.
Yeah, I would say possible to some extent. So I'm not an expert on the fluid MPC topic, but I have read some things about it. And I think the main concept is that you can, the computing parties can change across different, they call it epochs or different iterations. But I don't think it's possible to increase or decrease the number of computing parties in the fluid MPC papers that I saw. So it is something that's definitely that we are aware of in academia, but I don't think we have fully solved it yet. No.
Yeah, as also Thomas mentioned, we have fluid MPC there, but you should also imagine we always, not always, 99% we are considering outsourcing scenario. That means we have like 100 clients, it could be 1,000, it could be 1 billion. They will just secretly share the data and the computing parties can do the computation. So if you have the outsourcing scenario, that's perfect. We don't have any problem there for the dropout, for new users. But if you want to change that computing parties, yeah, as Thomas mentioned, we have active research. Also, some group by India, they're also working on it, and they're quite active there.
And sorry, before, does this come at the expense of big overhead in the protocol? If you're aware of this, is this costly in terms of overhead?
Wants to know what overhead?
So essentially, you have these different epochs and you reshare the data for the next committee, essentially. You have some handover procedure, but as Hossein said, usually you have millions of clients in a federated learning scenario, and if you expect that half of them drop out and are not there, like for the input and output parties, this is super simple to achieve and has literally no overhead. If you want to change these compute parties, which is usually 2, 3, you can forward secret share to the next committee or do some backup essentially. And this is somewhat, if you want to have strong security, you have to prove that you forward secret share your state, but it's doable. It's manageable.
Yeah, I think everything is said, but it will get costly if you want to change the number of computing parties. Input parties, totally fine.
Any question from the audience?
Thanks a lot for all the contributions. I have actually a quite related question, and this is, I understand that the math is understood, and I'm a computer scientist, and I find this very interesting to follow, right? And now having a more dynamic MPC in terms of math, yeah, great. Now, we are here in IPEN, and there's lots of questions, how do we get this to the practical side? And part of the practical side is, well, please don't take me now wrong if you're a lawyer, but there's also like the legal side to the practical side. And these dynamics, if I have a short look at the GDPR, I say, it doesn't support this. Even if you're here in Europe and you only have to get to the GDPR, right? It has like these clear roles, processors, data subject, and so on, right? How can we get to this fit? And now I make a very quick turn. Thomas said we are lucky to have public funding for this. I think this problem is not solved. It needs to be researched and it needs public funding, right? I mean, and there's the question, who is funding this for the next years? This is probably, I'm not sure whether you have ideas from the panel. Maybe it's a question for all around here in the room. Yeah. But this is my question actually for all here, and in particular for the IPEN community. Thanks.
Maybe another question, or we want to?
Thank you.
Thank you. So Michael Jensen, Karlstad University. Thanks a lot. Chiming in on what Stefan just said. So if you consider MPC as a PET, as a privacy enhancing technology, then we saw a lot of PETs that have been proposed as a famous idea. Then we have been spending decades on research projects evaluating how it could be done, but they never make it to become real world services, you know, like cloud services or something in the large scale use and uptake in the industry. So we have this kind of PET graveyard, if you would call it, or PET cemetery that actually has a lot of technologies. Speaking of voting, attribute-based credentials, all these technologies that have a lot of research history, but never really made it to become commodity off-the-shelf products. So what would be needed? GDPR compliance is one thing that I totally agree is a little challenging. Beyond that, what would be needed to get multi-party computations to actually become commodity things? Where's the problems? I think the problems are not on the crypto side. I think they are in different fields. And I would love to hear your experience on that.
Let's take another question. Fabio wanted to intervene.
Fabio, is there?
What I like of MPC is that it tends to divide the data and therefore divide the power that comes with the data. What I hate of AI and deep learning is that it tends to concentrate the data and therefore the power. The question is how far we are with the research on SMPC applied to AI when in the use case what you want to divide, what you want to secret share, what you want to distribute is not the input data but the model. Assuming, you know, the large scale model can basically absorb the data and it's Is this a use case that is being researched when you don't want the model to stay in just one hand, but would like to distribute among many hands? Is this a line of research? How developed is this line of research today?
Okay. Who wants to reply?
So maybe I can tell you about my experience for GDPR. Yeah, last year I had quite a headache to work with lawyers because I should explain them what is MPC, how it works, what is cryptography. And after 6 months, I was successful. And we worked with some lawyers for our human resource analysis. And yeah, we did a lot of work together. It was like 170 pages report, which we just summarized. 30 pages is online now. Yeah, I want to make it short. In summary, they told us MPC can be a game changer, and we can see MPC as an anonymization technique if we consider a specific application. But in the report, there is like 200 times, it depends, it depends, it depends. You know the lawyers, yeah? But it was a good hope, and they say, yeah, by using MPC, we can have a good solution for GDPR. And regarding your question, why we don't have MPC, I think we have. We cannot say we don't have it. For example, yeah, if you just check that MPC Alliance website, there's a lot of companies there, there's a lot of service there, and recently there is some company by UAE, they have MPC as a service in Amazon. They are using for federated learning. I was really happy to see that. But yeah, we have for more. And the problem is why we don't have it, maybe because selling privacy is hard. I signed a company. If you talk with the people about privacy, they say, yeah, we can just sign a contract. So then it's hard to talk about privacy and security. Always they talk about AI. Yeah, let's work on AI. That's really bad. And regarding your question, yeah, it depends on AI training or inference. For inference, we always consider encrypted models. That means we have sharing the model between different parties. And for my research, we can have, for example, something like ResNet 50 inference less than second in online phase. So that's possible for inference. But training is still, we have some bottleneck, which we are working on it in research domain.
I have a question to the audience. Who in the room has today logged into a website with a username and a password in a web browser? Okay, so you've been using MPC, you haven't seen it. All major web browsers these days check if your password is in a database of leaked credentials without really sending your password obviously to a server or downloading the entire database of data leaks. And under the hood, all major browsers use MPC technology to check your passwords. And this is rolled out by all the major platforms. Under the hood, you don't even see this. And these are brilliant use cases where MPC solves a non-trivial problem. You cannot just send hashes. Even the hashes leak substantial information about your password or your username. And this is being deployed on a worldwide scale. There's also for key protection, distributed signing, distributed decryption, and things like that. There are lots of startups also by many colleagues, Christian Rechberger, for example, sitting here, and others, having brilliant business use cases for MPC essentially, and therefore we need this decades of research. Like deploying such a system is a real challenge, but the mass has been there for years. The crypto has been there, and we have to explore new ideas and fresh ideas. And if we have a killer application, we can get rich, right? And if we have the time and have the killer application, there's a lot of VC funding also for that.
Yeah, so the GDPR question I think has been largely answered. What we found also quite nice in our pilot is the fact with MPC that, especially if you're based on secret sharing, that it only really works if you're all doing the same thing. So you really have to agree upon the functionality that you compute, which is also in the context of GDPR quite nice, that you cannot take your secret shares and do with it whatever you want, but it's really only fit for the purpose that you agree upon. So I think that's also a nice way how MPC can help with staying true to the GDPR. Then for the pet graveyard, I think what would also really help with, at least in the Netherlands, this is also a bit of a chicken and egg problem with standards or common language. On one hand, I think it can really help in the adoption of MPC if we would have some specification to refer to that everyone can understand and know that they're talking about the same thing. But standardization bodies don't always seem to be willing to standardize if it's not being used a lot already. So yeah, who's going? Yeah, it's a bit of a chicken and egg problem. And then for the machine learning one, we haven't done a lot. I think what we do use quite often is a combination between federated learning and MPC. So don't do the full training or split the model completely, but do a federated training and then use MPC to do the aggregation, for example, so that no single party learns the overall model. But I don't think that's what you meant completely. Maybe Cybernetica has an answer for that. I don't know. Please.
The AI part is not my really research avenue really. So, but I agree that we can do inference under MPC very well with cyclic models. Not a problem. Generally, training is still hard. I wanted to add to this, like, why are there no like MPC services, or why don't we like? Why there are not so many commercial offerings? It's I think well, you can basically buy MPC in a box, but then you have to deploy and develop the algorithm yourself, and this you can do. Come talk to us. But the problem why there are no public services is it stems from the core requirement of MPC. There has to be independent computing parties. So it's really difficult for anybody to offer like MPC as a general purpose service. Yes, you can do it if you're like staying in a domain, and this is what, for example, Joconda project is doing. So there are some rules and system operator and so on, but like general purpose, commercially available, like do whatever you want MPC service is difficult, because how do you show that there are independent computing parties? Without it, everything blows up.
I will not reply personally to the question. I will just, let's say, allow myself to offer a different perspective on anonymization, which is about, let's say, injecting uncertainty in the attribution of the data. SMPC is not for dealing with uncertainty. It's about splitting the data in order to do computation on exact numbers. So maybe during the coffee break, I will try to convince you that there is a different angle from which anonymization can be tackled. With this, I would like to thank our distinguished speakers and ask you to make an applause to them, to greet them. And, thank you very much.